Okay, YouTube, in this video we're going to continue to explore how we could use factoring as a method to help us solve trigonometric equations. Now in the last video, we had utilized greatest common factor in order to factor, say, a sum or a difference on one side that was set equal to 0, so that we could set all of our factors equal to 0. In this video we're going to be looking at is a specific type of situation that is going to look very similar to some algebraic factoring that we've done before, but also to factor and help us solve these trigonometric equations. So I guess the first thing I want to point out is this. With these two trig equations that you see here, if somebody were to ask you to solve for the angle, it's a little bit difficult to do just because of the fact that we have sine squared and a sine to the first, and that those things are not like terms. They don't combine. And so since that's the case and they do not combine, it's hard to isolate one or the other of these signs in order to use inverse trig functions and find the angle. So our method is going to be to factor this. Now, one thing I want to mention is that this algebraically, if we were to say x is equal to the sine, that would be redundant. I'm not going to say x is equal to the sine of x. What if I said u is equal to the sine of x? Then it's pretty clear that we could rewrite this as the sine squared minus 2 times the sine minus 3 equals 0. And the thing that I recognize about this is when I factor it, we can factor this because it's a trinomial in this quadratic form. So we say u minus 3, u plus 1. These would be the factors here. And at this point, we could simply just take each of our factors and set them equal to 0 and solve them individually. And so I suppose we would get that u is equal to 3 and u is equal to 1, negative. And so one thing that I want to kind of point out here is that all of this method that we saw just here, by making a substitution with u and sine of x, we're going to do the same thing, except for we want to be able to factor this in the form that it's currently in. So instead of having u's, what we're going to do is we're going to put clearly in our sine of x's here, because sine of x is the same thing as what we were using to represent with u. So when we have u minus 3 and u plus 1, really what we're saying is we have sine x minus 3 and sine x plus 1. And again, setting each of these factors equal to 0 and solving them, what we're going to end up with is that sine x minus 3 equals 0, or sine x plus 1 equals 0. Likewise, we could say sine x is equal to positive 3, and also that sine x is equal to a negative 1. So I'm going to put boxes around these and say that, look, we've isolated our trig functions. Now, if we were to take, say, the sine inverse of both sides of this equation, we would get that x is equal to the sine inverse of 3. And so, this would be tantamount to asking, what angle was it that when we took the sine of it, we get 3? Well, recalling from your unit circle, your radius of your unit circle, we have a radius of 1. And so if our sine values are all these y values, then there does not exist an angle that when we take the sine of it, we ever get 3 for an answer. The biggest sine ever gets is 1. And so we would say that this has no solutions. Now, with respect to this other equation over here, no solutions on this one, we'd say here we get x is equal to the sine inverse of negative 1. We're saying what angle between 0 and 360 could we take the sine of and get negative 1 for an answer? And of course, our y values down here at 3 pi halves is the one where sine equals negative 1. So we say 3 pi halves plus lengths of its period, or the solutions right there. So now, taking a look at this next one here, we say 2 cosine squared beta minus cosine beta minus 1 equals 0. Excuse me. The interesting thing here is that when we factor this one, because the a value is not simply a 1, we can't say, can we think of two factors of, say, a negative 3 that add up to be a negative 2, and those are the values we put in. That's not going to work for us here. What we're going to need to do is a little bit of guess and check. And so what I mean is, let's start with our 2 cosine squared beta. What would we need to put in place in front of each of these sets of parentheses so that when we multiply them, we get 2 and a cosine squared of beta? So as I kind of think about this here, we'd have to have, a 2 cosine beta, getting ahead of myself there, times a cosine of beta. And so multiplying these, we would get our 2 cosine squared beta. Now, looking at the rear side of things, we would say, what two numbers could we multiply to get a negative 1? And so this is kind of a crapshoot. I could say positive 1, negative 1. Thing here is I'm not sure if these factors work. So, checking the first part of our FOIL, the F part, F-O-I-L. Of course, F works out. We made sure that happened. 2 cosine beta times cosine beta is 2 cosine squared. The L part we made sure happened. We say 1 times negative 1 is negative 1. The only part we haven't checked are the O and the I here. And so we're going to check our outer and our inner multiplying here. And if we were to do that, we get 2 cosine beta times a negative 1, which would be a negative 2 cosine of beta. And we get a 1 times a cosine of beta, which is a positive 1 cosine of beta. When we add these together, we get a negative 1 cosine of beta. And so looking back at our original expression, we could see that, yes, that's actually what we wanted to get in the middle there. Now, if we hadn't have gotten this, the idea would have been, well, maybe we switch the positive and negative around and check our outer and our inner again to make sure it works. But these work. And so what we're going to do is we're going to take 2 cosine of beta plus 1, this factor here, and we're going to set it equal to 0 and solve it. We're also going to set cosine of beta minus 1 equal to 0 and solve. So let's go ahead and start by isolating the trig functions. Make short work of this one. Kick the 1 and divide by 2, we get a negative a half on the right. And it's true that taking the inverse, cosine of both sides, we get the cosine inverse of negative a half on the right. So this is our angle here. Over here, if we add the 1, we get cosine beta is 1. Then our angle must be the angle that when we took the cosine of it, we got 1. So we say cosine inverse of both sides, we got cosine inverse of 1. So working backwards here, we say if cosine came out to be negative, looking at this here, if cosine were negative, what quadrants, first of all, would we had to have terminated in? And we'd say, well, cosine negative would mean I couldn't be in the first quadrant and I couldn't be in the fourth quadrant. So it would have to be here or here. And with respect to the reference angle, we'd say, well, where is cosine equal to a half at? I believe that's at 60 degrees or a pi thirds. We say cosine is a half at pi thirds. And so we would say that knowing that our reference angles are pi thirds apiece, then I could say, well, then our angles in standard position must have been 2 pi thirds. We'd say 2 pi thirds plus multiples of cosines period. But also, beta had to be equal to, now, pi thirds past pi, which would be 4 pi thirds. 4 pi thirds plus 2 pi k. So here are solutions from that part of our equation. Looking over here, we say, where is cosine equal to 1? It's kind of one of my favorite questions because there's only one spot on the entire unit circle where cosine is equal to 1, and that'd be at 0 radians. We say beta is equal to 0 radians plus multiples of 2 pi, which is the period of cosine.